My name is Loukidis. I'm a PhD candidate on my third year, and we'll be presenting our work regarding the correlation of acoustic emissions and pressure simulated currents recording when alpha stone specimens were subject to three-point bending. I will keep it short. Our main aim is to investigate the role of the specimen's porosity when alpha stone specimens are subject to three-point bending with the aid of the pressure simulated currents and the acoustic emission technique. The acoustic emission technique, the acoustic emissions refer to the transelastic waves generated by the sudden energy released when structural changes occur in the back of material. We'll keep it very short. We'll study the acoustic emissions. We will study the acoustic emissions through the temporal evolution of the improved B value. And regarding the pressure simulated currents, is a non-destructive testing technique, which is based on the emitted electrical signals, which could be attributed to local polarization disturbances that are caused in the bulk structure by an external applied mechanical loading. The characteristics of the specimens, first of all, alpha stone is a very homogeneous limestone from Crete, a village called Alfas, that's why it has the name. Our specimens were prismatic of 450 millimeters with a square cross section of 100 millimeters. We had two classes of specimens, one with high porosity, class A, and another one, class B, with low porosity. The porosity was calculated using the liquid absorption method. Here we can see our experimental setup. We had concurrent measurements of acoustic emissions and electric currents. We used 6 acoustic emission sensors, and at the bottom of the specimen, we used 2 cold-plated electrodes in order to measure the electric current emitted during the crack propagation. And we synchronized both measurements through the loading, through the imposed mechanical loading. Because Alfas stone presents some difficulties in order to measure the acoustic emissions, we modified according to the manual of the manufacturer for the acoustic emission detection system some parameters. Here you can see them. And now I present you the experimental results regarding the class A specimen. Figure A shows the temporal evolution of the recorded PSC signal, black curve, in juxtaposition with the applied load. You can see that during the last stages of the loading system, around 1,000 seconds, a very steep increase of the current is observed. This is in accordance with the recorded amplitudes of the acoustic emission hits, where we see that from the 600 second and afterwards, the acoustic emissions are the rise of the PSC follows the same trend as the acoustic emission hits. At the bottom, we see the cumulative energy of the acoustic emission hits versus the recorded PSC signal, and at the figure D, we see the cumulative heat count of the acoustic emission hits. Moving on, we see now for the class B specimen. The class B is the one with the low porosity. As you can see, we have a greater number of recorded acoustic emission hits. Notice that note that whenever the PSC signal exhibits a peak, not a peak, yes, let's say a peak. We also observe some high amplitude acoustic emissions. Moving on, now I present you the comparison between improved value and the PSE for each specimen class. No, I should mention first of all that in class A, the specimens, the B value was calculated using a relatively low number of 20 acoustic emission hits, and each next IB value was calculated by a shift of 1 acoustic emission hit. Whereas for the class B specimens, the number of acoustic emission hits that were used were 50. And each next group was calculated by a shift of 5 acoustic emission hits. This was done because in class A specimens, those with high porosity, the number of acoustic emissions were lower than the total number of the code acoustic emissions were lower than the class B specimen. I would like you to note what else. On the left figure, we only plot the last stage.
Andronikos, sorry, but you have to speed up your presentation because we are very late.
Yes, I'm sorry. I felt that I was too fast.
No.
Okay, sorry. Some major remarks. First of all, the class A specimen, those with high porosity, were at 12 kilonewton. The fail load was at 12 kilonewton approximately, whereas for the class B was at 18 kilonewtons. As I told you before, for the class A, we had less acoustic emissions than in class B, and the maximum value of the recorded PSE was lower for the class A, whereas for the class B was higher. Concluding remarks, our findings depend. We've seen that both the PSE and the acoustic emission cycles depend at least quantitatively at the density of the specimens tested. Both acoustic activity and both acoustic and electrical activities are quite weak in the case of the high porosity specimens in relation to the low porosity specimens. Also, the IB value obtains the deterministic behavior before failure, and the results so far support an at least quantitatively correlation between both techniques. And certainly additional experiments will be conducted before definite conclusions could be drawn. Thank you for your attention. I hope I wasn't too fast. And that's it. If you have any questions.